Now we're going to revisit our infinite sheet of charge. So we're going to say this infinite sheet of charge is on the z equals 0 plane, as I've attempted to draw in here, and we're going to assume that it has a uniform charge density rho sub s. And what we want to figure out is what is our electric flux density at some point p. And so I'm going to put this arbitrary point up here above our plane, and I'm actually going to move this p a little further away just so that when I'm drawing my Gaussian surface, it doesn't get in the way. So we have our Gaussian surface, which is what we want to choose to apply Gauss's law. And remember, we want our electric flux density d to be constant on that Gaussian surface. And we want d to be normal or tangential. And so we can think about what type of Gaussian surface we want here. And we can think about this arbitrary point P moving about, and we could say, well, it's not going to depend on rho. So as we've talked about before, we know that generally we're going to have our field direction pointed away from our sheet and not in either of the other directions, sort of to the left or right, but purely up. And so what we can say then is that's not going to depend on rho or our r, our radial distance from the origin. So we might think, yeah, it should depend on z, how far away we are from the sheet, and we'll come back to that here in a little bit, but certainly we can see that our charge density depends on z, but that's the only thing it depends on. So if we're at z equals 0, we have the charge density of our charge sheet. If we're at any other z, we do not have that. So because of that, we're going to say that we have rectangular symmetry, and we're going to use a rectangle for our Gaussian surface. And so I'm going to draw this rectangle such that it's half above and half below the sheet. So again, sort of bear with me here as I attempt to draw this, but we're going to draw our, let's see if I can start better than that. We're going to draw this sort of arbitrary Gaussian surface such that our point P is on the top of this rectangle. And then we're going to have it going down to our sheet. So something like this. And so in the back, this is coming like that. And then we're going to have another part of our Gaussian surface, which is going to be sort of equal length below our z equals 0 plane. So something that looks like this. All right, so this is half above, half below, and that's going to account for any dependence on z, right? Because if we sort of intuitively expected dependence on z, we'd say, well, this top surface here is the same distance as this bottom surface from our sheet, so they should have the same electric flux density. So we have a rectangle which is half above, half below, or we could also say that it is bisected by that infinite charge sheet. Okay, so of course with this rectangle we're going to have 6 sides to consider. So we have sort of our right side, our back side, our front side, and our left side. So I know that's kind of hard to visualize just with those dots. But we basically have the 4 sides, and then of course we have the top where P is, and we have the bottom, which is the opposite. And so as we know, our ds is going to be pointing outward from the volume, so we're going to have our y direction. In the back, we're going to have our negative x direction. In the front, we have our positive x direction. And here we have our negative y direction. And of course, all of those, like we've already talked about, our d is just going to be in the z direction or the negative z direction, depending on whether we're above or below the infinite sheet. So in this case, because our point P is above, we can say we know d is equal to just the z component. All right, so basically what that means is we're going to get, when we do the dot product for our integral, the terms for all 4 of our sides are going to be d dot ds equals 0. So for 4 sides, we have that our d dot ds is equal to 0. And so we have no contribution to our flux from those sides. So we then want to look at the top and bottom. So we can say that our total charge enclosed is going to be rho s times the surface integral of ds, and that's equal to q, so our total charge enclosed. And then from Gauss's law, we know this is also equal to the charge over the the integral over the closed Gaussian surface of d dot ds. And so what we've said is we know that the four side terms are going to go away, so we just have the two top terms to consider, or rather the one top and the one bottom. And because our d is going to be constant, what we can say is we can go ahead and pull out that electric flux density from our integral. So we get that our d dot ds is just ds times dz. We're going to pull the dz out, and now we're going to have an integral over the top surface, ds, plus the integral over the bottom surface, ds. So let's just sort of arbitrarily say that we have some cross-sectional area here and here of A. So let's say cross-sectional area A. So if we assume that, then what we have is our enclosed charge is going to be rho s times A, because that's the integral of our surface over the differential surface is just going to be A, equals Q, which is equal to, from our integral over here that we left, is just going to be dz times A plus A. And so we can solve that for our d, because we know, as we've already argued, it's only going to be in the z direction. So our overall d is going to be rho s divided by 2. And notice we have the a term canceling out, and we have that in our z direction. So we can compare this to the result we had previously on page 413. And just as we saw there, we have no dependence on the distance from our charged sheet. So we set up our Gaussian surface such that if we did have dependence on that, it would have been accounted for, but we see that it's actually canceled out. So there's no there's no dependence on the distance from the charged sheet. And we also see that the cross-sectional area of our Gaussian surface doesn't affect the calculation either, as we would expect.